Hello everyone, so today I would like to present on my assignment project, which is weather forecasting and climate modeling with differential equations. This topic is crucial because it will understanding weather patterns to help us to predict climate changes. It will prepare for extreme weather and improve environmental planning. This will include the introduction, problem statement, methodology, computational solution, discussion, and conclusion. In this presentation, I will cover the mathematical model and computational solutions and also discussion on the results to demonstrate how this equation will stimulate the real-world weather patterns. Weather forecasting relies on mathematical model that describe on how temperature, pressure, and other atmospheric variables change over the time. Among these models, differential equation plays a key role, particularly in partial differential equation, such as heat equation and the wave equation. So, for the problem statement and literature review, this primary goal for this project is to examine on how differential equation, specifically the heat and wave equation, can be used to describe and predict the changes in temperature distribution over the time. By simulating this equation, I aim to understand this behavior and their application in weather prediction. So next, I will talk about the methodology. For heat equation is for temperature distributions. So here is the heat equation for this model. This equation shows how temperature diffuse over the time. This represents the temperature and the alpha is the thermal diffuse, which determines how fast the heat will spread. For the wave equation is for pressure, the variation of the atmosphere. This equation model shows how atmospheric pressure will propagate. The variable represents the pressure and the c is the wave speed, which determines how fast the disturbance moves. By solving this equation, I use the method and implement in the Wolfram mathematical model, which allow me to appropriate their behavior over the time. So now let's move on to the computational solutions. For this computational solution, I implement and visualize the different equations using the differential equation method, and I implement the heat equation and the wave equation using Wolfram cloud. Okay, from this heat equation, I break it down the code, and firstly, I define the function which is U, S, and T and set the thermal diffusivity alpha equal to 0.01. Conditions by ensuring that temperature is 0 at the ends of the domain, which is x equal to 0 and x equal to 1. For the initial condition, I assume a sinusoidal temperature distribution, meaning that the heat starts to concentrate in the middle. Finally, I use the mathematical functions to numerically solve this equation over the time. By visualizing this result, I generate a 3D surface plot showing on how the temperature evolves over the time. As expected, the heat spread gradually and eventually reaching an equilibrium state where the temperature is evenly distributed. So, high diffusivity value shows how the result in faster heat distribution. Choosing the correct time step is crucial because too large a step leads to instability, while too small will increase the computational time. Next, I will examine on how wave equation models shows how pressure disturbance will propagate. The equation is shown in the methodology previously. So now, let's break it down the code. I define the function P, S, and T and set the wave speed c equal to 1. The boundary conditions will ensure that the wave is fixed at the both ends s equal to 0 and s equal to 1. It will make a convenient system. For the initial condition is again a sinusoidal shape, that meaning the wave will start as a single oscillation. For the result, I generate a 3D surface plot to show how temperature evolves over the time. X-axis represents the position of X along 1D spatial domain. This could be simplified to the representation of air pressure in the atmosphere over a time certain distance. For Y-axis represents the time, showing how the wave propagates over the time, and the Z-axis is a color map to represent the pressure amplitude but the difference to value that indicate the varying pressure intensities. I observed the oscillations where pressure increase and decrease periodically, demonstrating the wave-like behavior. Even reflecting occur at the boundaries that we confirm that the system is constrained. If the wave speed were higher, the oscillations would travel faster. Next, let's discuss the key findings. For the heat equation results, the heat equation simulating on how the temperature spread gradually due to the thermal diffusion, eventually to stabilizing at an equilibrium state. A higher thermal diffusivity alpha results in faster temperature distributions, aligning with the expected heat condition behavior. For computational challenges include the need for small time steps to maintain the numerical stability. For the wave equation results, the wave equations will stimulate to demonstrate on how pressure variations traverse as the wave and maintaining a periodic oscillations. A higher wave speed, which is c, will result in the faster wave propagations, while boundary conditions will create a reflections in effects. Computational accuracy depends on how choosing an appropriate step size to prevent the instability. So let's summarize everything in our conclusions. In summary, my computational results confirm that the differential equations effectively model weather patterns. The heat equations will explain the thermal diffusions, showing on how the temperature spreads and reach the equilibrium. For the wave equations models, pressure variations demonstrating oscillatory behavior in the atmospheric systems. These equations form the basis of modern weather predictions model, in which incorporate additional factors such as wind dynamics, humidity, and external forces. Higher dimensional models will have more realistic weather simulation, and the machine learning technique will enhance the prediction accuracy. This will improve the computational efficiency. I think that is all for me. Thank you.